Hello guys, in this video we're going to discuss about maximal ratio combiner, a very important topic in wireless communication, and I'm going to do how ML decoder, like why are we opting for MRC, like maximal ratio combiner, we can call it as MRC in short, and how ML decoder is MRC, like maximum likelihood decoding is the best decoding that we can do at any point of time. So we'll have to basically prove the fact that maximum likelihood decoder is basically MRC and the performance analysis of MRC. All right, these two things I'll have to prove. So the scheme, I need to specify the scheme. The scheme is on the time axis I'm sending the same symbol L times over L channel or some kind of repetition coding. So there exists a time difference TD between two symbols, two consecutive symbols to be more specific. TD, this all I need to make sure is TD has to be greater than TC, where TC is what? Coherence time. So coherence time is defined as the time for the time taken by channel, time taken, minimum time for this matter, time taken by channel to change its channel coefficient, to change its channel coefficient. All right, so all I have to make sure is I need to make sure that I will wait for the particular time TD. I'll have to wait for some time TD which is greater than or equal to TC, which is at least TC, and it has to be greater than TC. And why do we need to? The first question is, why do we need to make sure that the symbol time, the time difference between two consecutive samples has to be greater than TC? This is the obvious question to ask. The answer for that question is we need channel coefficients to be independent and uncorrelatedness. Obviously, I do know the fact that independence refers uncorrelated all the time, but I'm specifying this uncorrelatedness to make sure that, because I would like to look at this with putting more emphasis on uncorrelatedness. All right, because this makes sense for me. I'll try to why do we need to make sure that channel coefficients are uncorrelated? That you'll get to know at the end of the session. So this is one of the benefits that we're looking forward. We need to make sure the channel coefficients are uncorrelated. All right, and also we also know the fact that TC is inversely proportional to velocity of the receiver. This is velocity of the receiver. One essential thing we need to observe here is TC is putting limitation on the data rate of our scheme, right? TC is putting limitation on data rate of our scheme. All right, because lesser the velocity, more will be TC. More will be, if TC is more, the waiting time that we have to the time we have to wait is getting increased more and more. So in that scenario, if you send a symbol X, you'll have to wait for a longer and longer period of time for the stationary receiver. So once the receiver is stationary, you'll have to wait for longer and longer period of time to make sure that channel coefficients that we got are IID and uncorrelated, right? So it really depends upon the velocity of the receiver that we're dealing with. Okay, because why do we need to make sure that all the channel coefficients are IID? That we will get to know in the later part of this same lecture. So let's write down the equations. Let's go ahead and write down the equations. Y1 equals to H1x plus N1. By the way, I can specify single transmitter, really simple single transmitter, single receiver. So this transmitter, this is receiver. All right, and H1 for the instance is H1, H2, and so on. Hn IID Cn 0,1. This is assumption, and N1, N2, and so on. NL IID Cn 0, square. Alright, Cn means complex quotient random variable. Okay, So y2 equals to h2x plus n2, yl equals to hlx plus nl. So this is basically, we are transmitting the same x, transmission of same x over L time instance. Alright, so first of all I need to make, so what do we do now? This is the first question. So to answer that question, straight away jump into the ML detector, and also one more important thing we need to make sure here is y1, y2, yl are also independent. In fact, y1, y2, yl are also independent. Yeah, this comment will suffice as of now. And so y1 has absolutely no dependence on y2, y2 has absolutely no dependence on yl. Alright, so ML detector basically probability of y, received y, given the fact that we know the channel matrix H and A. This is a very important assumption I forgot to mention. Whenever we're doing the maximal ratio combining, it does mean we know CSI. CSI means channel state information. So this inequality is obvious to write. You have y given h bar. What I mean by bar is a vector. I'm indicating a vector, so it has to bar also here also h b. Right? Given that we know the channel coefficient, channel CSI, given that we know the transmitted symbol is A, what is the probability of event Y, given that we know these two things? So, alright, the same thing. So this is basically ML rule that we have to follow. Receiver have to know, because once we know the rule, then only we can decide whether the transmission is A, the symbol A, or the symbol B. Alright, once we know this, once you figure out this rule, this rule really determines what is A and what is B. So for the receiver we have to specify a mathematical inequality in such a way that it can decide, depending upon the output, depending upon the input that it receives, it can specify whether it can decide basically whether the receiver got the symbol A or the symbol B. Alright, so it is like probability of y1, y2. I'm just expanding the vector yl, given that h bar A greater than A, less than B. I'm not going to do the full derivation. I'll skip the algebra, but I'll definitely give the approach to do it. Yl given h bar and B. Alright, so given that we know A is transmitted. Alright, so what is y1 equals to h1x plus n1, right? So we know A is transmitted, so y1 equals to h1a plus n1. Alright, so the event of y1, the probability of occurrence of the event y1, given that we know A is transmitted, has the same probability of occurring of this event, probability of n1 equals to y1 minus h1a. So my statement is probability of y1 given h1a is nothing but probability of n1 equals to y1 minus h1a given h1a. Alright, so we know that noise is independent of the channel matrix H, and it is also independent of the signal, the symbol that we have transmitted. So we can get rid of this conditional. So that is the aim. That's why we'll switch for noise terms, because that makes life easy. So probability of n1 equals to y1 minus h1a equals to probability of y1 given h1 comma a. Alright, so if we know B is transmitted, B is transmitted, same thing, you replace probability of y1 given h1b equals to probability of n1 equals to, maybe I'll call it n1 tilde equals to y1 minus h1 to b. Alright, so and also we also specified the fact that they are all, y1, y2, yl are independent, the transmissions are independent, the receptions are independent. y1, y2, yl equals to probability of y1, probability of y2, probability of yl. This follows from independence. All right, we know the fact that now the inequality will be boiled down to probability of n1 into probability of n2 and so on. Maybe I'll write one step ahead. Probability of replacing y1 with y1 with, I will replace y1 with this, essentially this probability. All right, so probability of y1, y2, yl given h bar a equals to probability of y1 given h1 a into probability of y2 given h2 a, probability of yl given hl a. All right, so probability of y1 given h1a, probability of y2 given h2a, probability of yl given h1a, and we also know the fact that from the above analysis, probability of y1 given h1 into a equals to probability of n1 equals to y1 minus h1a, right? You can get rid of this conditional because noise is independent of channel and the symbol that you transmit. So basically, probability of y1, y2, yl given h bar a equals to probability of n1, n2 and so on, nl, and noise terms are dependent, probability of n1 to probability of n2 into probability of n1. All right, so we know the fact that PDF of n1, because n1, n2 up to nl are IAD cn0 sigma square. All right, so PDF fn of n equals to 1 by pi sigma square exponential of minus n square by sigma square. All right, so all you have to do is replace n by, if it is, let's suppose if it's n1 fn1 of n1, 1 by pi sigma square exponential minus n1 square by sigma square, fn2 of n2 1 by pi sigma square, same thing, exponential of replace minus n2 square by sigma square and so on. All right, we also know the fact that n1 equals to y1 minus h1a. All right, n2 equals to y2 minus h2a. You can essentially replace all these things, and the same thing for so the rule, I will write down the rule, probability of n1, probability of n2 and so on. These are PDFs. All right, because n1 is a continuous random variable, so these are PDFs. A, B, probability of n1 tilde, probability of n2 tilde, n1 tilde. All right, so if you if you do this algebra, the deciding rule will boil down to this equation: I equals to 1 to L yi hi star greater than less than a b 0. All right, so this is important. So this is ML rule, and this is also what MRC does. Because essentially what it is saying, essentially you'll receive y1, multiply with h1 star, plus you receive y2, multiply with h2 star, and do it L times because we're transmitting L symbols, hl star, and take the real part of it. If it is greater than 0, it is A. If it is less than 0, it is B. All right, so these are the rule that you have to remember. So we can easily do the construction of MRC now, right? So MRC, so you will get y1, h1 star, same obvious stuff. So h1 star, sum it up, y2, h2 star, sum it up, yl, hl star, sum it up, and essentially get, and there will be decider, two-level decider. If it's greater than 0, it is A. If it is less than 0, it is B. So it's the output of MRC. Alright, so we're done with the first part of the video, which is ML decoder for MRC, and we have proven the fact that MRC is nothing but ML decoder. Performance analysis of MRC. Performance analysis MRC. So y1 equals to h1x plus n1, y2 equals to h2x plus n2, and so on. YL equals to hlx plus nl. All right. So I will just try to perform the MRC. Y1 h1 star plus y2 h2 star plus YL HL star equals to mod of h1 square plus mod of h2 square. I'm skipping a couple of steps of algebra. H square to x plus h1 star n1 plus h2 star n2, and so on, hl star nl. All right. So the easiest way to derive probability of error, the thing that which is important to derive here is diversity order. All right. What I mean by diversity order, we'll get to know. But diversity order is one of the criteria. So I'll try to define the diversity order vaguely. If probability of error turns out to be 1 by SNR power L, turns out to be some constant into 1 by SNR power L, this L determines diversity order. Alright, if L is more and more for less SNR, you see, if L is 5, there are two cases. If L is 2 maybe, L is 4. If L is 4, let's suppose you have L is 4. For this case, for the least SNRs also, as the power is more, the whole number will turn out to be more, and the probability of error will turn out to be less. Essentially, for the least SNR, as L is more, least SNR gives rise to less probability of error. Alright, relatively, I have to write relatively, otherwise this statement won't make sense. Like if L equals to 4, L equal to 2 to make more sense, and SNR equals to what? Let's suppose SNR equals to, like, I'm just playing with the numbers. SNR equals to 2. Don't try to make sense out of these numbers. Just try to make a point. I'm trying to make a point. So probability of error here is what? 1 by 2 power 4, right? 2 to the 4, 8, 16. 1 by 16. And probability of error here for the same SNR, 2 by 4. Alright. So for the given signal power, because noise power you can't control, for this given for the given signal power, the system which has high diversity order is offering much less probability of error when compared to the system which has higher diversity order, which has lower diversity order. So we want diversity order to be higher. All right. So the easiest way to derive I'll have to say easiest way to figure out diversity order is figuring out SNR. Alright, and if you want to derive exact bound, and you obviously you cannot find out the exact probability of error, like which turns out to be, you can do it, but which turns out to be a nasty, we will end up with a nasty expression that we don't want. We want to figure out the bound. We want to figure out the upper bound of the probability of error. So deriving the diversity order through figuring out bound of probability of error is a tougher task. I will do it in this session. Is a tougher task until unless someone asks you to do it. You can do it, but from probability of error expression you can directly find out diversity order. This is the one way. That another easiest way I find it much more easier is to find SNR. All right. So start with the equation y equals to, this is the output of MRC, h1 square, h2 square, and so on, hl square into x plus h1 star n1 plus h2 star n2 and so on, hl star nn. Right? What is the SNR? And call this whole thing as n tilde. What we know, n tilde equals to h1 star n1 plus h2 star n2, so on, hl star nl. All right. So expectation of n tilde is 0 because expectation is linear. We know h, so it's no longer a random variable. You know h, and expectation of n1 plus expectation of n2, everything boils down to 0. And sigma n tilde square, variance of sigma n tilde square, as n1, n2, nl are independent, you can basically add the variances. h1 is mod of h1 square, sigma n1 square, mod of h2 square, sigma n2 square, and so on, mod of hl square, sigma nl square. All right. And we know the fact that as their IID, sigma n1 equals to sigma n2 equals to sigma nl. So mod of h1 square plus mod of h2 square and so on, mod of hl square into sigma square. Alright. So what is the probability of error is signal power by noise power, right? So signal power, as we're treating h as constant, because we know h, so you can treat x as constant. Sorry, you can treat h as constant. So probability of error is signal power. Signal power is what? Assuming the signal power is p. Let's suppose x has a power p. If you multiply with any constant ax, the power has to be a square into p, right? So by the same logic, you can call the whole thing as chi square into p by noise power. What is noise power? Noise power is what? Expectation of x square minus expectation of x whole square equals to variance sigma x square, right? So this is total power. This is DC power. Total power minus DC power equals to AC power. So we want total power. As the mean of the random variable is 0, mean of the noise random variable n is 0. This goes to 0. All right. So all we are left with is expectation of x square is nothing but variance of the total power equals to AC power, because there is no DC power. So what is variance of the noise? Variance of the noise equals to what? Variance of the noise equals to, we have done this, right? This is what? Chi times sigma square, because we have defined the fact that h1 square plus h2 square h square equals to chi. So this same chi is showing up here. All right. So chi into sigma square. So signal probability of error equal to signal power chi square into p by chi sigma square equals to chi p by sigma square. All right. These are SNR, and chi is what? Mod of h1 square, mod of h2 square, and so on, mod of hl square. All right. Yeah. The number of diversity order, to figure out diversity order, number of IID channel coefficients, number of IID channel coefficients which are in the variable chi, is nothing but diversity order, right? So number of channel coefficients which are IID. So chi is a function of some random variables, some set of random variables, and we have to count number of IID random variables in that function chi. So the number of IID random variables in the function chi is nothing but diversity order of the system. All right. So we make sure in the beginning of the session I made this point clear that we made sure that TD is greater than TC. So all the channel coefficients H1, H2, HL are IID. So we are pretty sure that all the coefficients that are involved in the function chi are IID. So the diversity order, diversity order of the system is L. All right. So I'll try to make I'll try to give a intuition behind it. Like why do we need why diversity order is a function of IID channel coefficients. All right. So if you really look at this expression, chi into p by sigma square, where chi is a function of h1 square is a function of h2 square and so on hl square. All right. And let's try to take, let's suppose they are not independent, right? Let's try to take extreme dependence case. What is extreme dependence case? H1 equals to H2 equals to HL, right? So these are essentially same. If they are essentially same, that is the extreme dependence that we can assume. All right. If this is the case, if H1 goes to deep fade, all right. So if H1 goes close to 0, so as H2 and H3. H2 will go to 0, H3 will go to 0. Essentially up to HL will go to 0. All right. So our signal power is safeguarded by channel coefficients H1, H2, HL. All right. Our signal power is safeguarded by, you see, this is a signal power. You can consider this whole term as effective signal power. P effective equals to chi into P. All right. If H1, H2, HL, if they are not IID, if they are not IID, all right. So if H1 goes to, if one of the channel coefficient goes to deep fade, it will make sure that all of the channel coefficients will go to deep fade, right? Because they are not IID. Because they are not independent. So if H1 goes to 0, it is obvious that H2 will be close to 0, H3 will be close to 0, and H4 will be close to 0. Considering the fact, and you see, we started with the case of extreme dependence case. Once we started with the case of extreme dependence case, once one channel coefficient is going to 0, all of the channel coefficients are going to 0. This is not what we want. All we want is, if H1 goes to deep fade, we don't want all of the coefficients to be in deep fade. What I mean by this is, let's assume a scenario where diversity order is 2, p by sigma square mod of h1 square plus mod of h2 square. All right. So if h1 and h2 are IID, h1 h2 are IID independent, they are independent. That means h1 has nothing to do with h2. All right. That means if probability of h1 equals to 0, so sorry, if probability of if h1 and h2 are independent, that means probability of probability of h2 going to 0, given that h1 equals to 0, is extremely close to 0. All right. So there is very little chance that if h1 goes to deep fade, h2 will always also in deep fade. There is very little chance for this particular event, given that they are independent. So if h1 and h2 are independent, if h1 goes to deep fade, h2 will come into rescue, because independence will make sure that independence makes sure that if h1 goes to 0, h2 is not it does not have to be 0. If h1 equals to 0, if given that if h1 h2 are IID, if probability of h1 equals to 0, given that probability of h1 equals to 0, probability of h2 equals to 0 will be close to 0. All right. As they are IID, so if h1 goes to deep fade, my SNR is still good, because p by sigma square, h1 is 0, but h2 is still there to scale my signal power up. That's what I want, right? Because essentially I need signal to noise ratio at the input of the receiver has to be higher. I need to make sure that it has to be higher. So I have one more coefficient as my diversity order is 2, as h1 tends to 0, I have at least one more coefficient to safeguard my signal path. All right. If they are dependent, then if h1 goes to 0, SNR is p by 0 plus 0 by sigma square, because this is the case of extreme dependence. If h1 goes to 0, h2 has to be 0. So 0 plus 0 is 0, signal SNR is 0. All right. This is not what we want. We want IID, because if h1 goes to 0, we are making sure the fact that h2 is not equal to 0. So IID plays key role, maybe independence, to be more precise, independence of channel coefficients is determining diversity order. All right. So the whole procedure is you write down these equations. I'll have to start with here. Yeah, you write down these equations. This is the first step. Second step, do MRC. Second step, and figure out SNR. I figured out SNR here. Yeah, this is the third step. All right. Once you know what is this factor chi, you can write it as h1 square, h2 square, and hs square. Number of IID random variables in this factor chi is nothing but diversity order. All right. So once we know diversity order is L, you can directly write probability of error is proportional to 1 by SNR power L. This is obvious. This follows from the first factor. Because you can relate, right? Because if the received SNR is low, probability of error has to be higher, right? So our channel coefficients are safeguarding the SNR, even though there are couple of channel coefficients are close to zero. We're making sure that our diversity order has this capacity to compensate two deep fading channel coefficients. So there are L minus 2 other channel coefficients which can compensate for those two fading coefficients which are going to zero. And we modeled, and this is also standard fact that H1 is a complex Gaussian random variable, Cn 0, 1, right? So if H1 is Cn 0, 1, mod of H1 square is exponential 1. All right. So probability of mod of H1 square greater than less than 1 by SNR. This event is said to be deep fade event. This is equals to 1 by SNR itself, approximately. Because it's an exponential random variable. Exponential of mu is nothing but what? What is the PDF exponential of mu? 1 by mu exponential minus d by mu. Alright. So probability of capital X less than or equals to 1 by SNR equals to minus infinity to 1 by SNR exponential x dx. And exponential is a positive random variable. So low element is 0. So exponential of x is integral exponential of x is again exponential of x. Exponential of x is 0, 1 by SNR. So the exponential of 1 by SNR minus what? Exponential of 0 is 1. Alright. So 1 by, I'm expanding this 1 by SNR power 1 factorial plus 1 by SNR whole square by 2 factorial and so on, and minus 1 I have, minus 1 cancel. So assuming the fact that SNR is high, SNR is sufficiently high, 1 by SNR is sufficiently low. Alright, so we can neglect these higher order terms. So essentially it turns out to be approximately 1 by SNR. So probability of I will try to give another insight on this thing. So probability of, let's suppose I have two systems. One have diversity order L equals to 2. One has diversity order L equals to 3. So probability of errors SNR equals to SNR at the input of the, to be more precise, SNR at the input of what? At the input of the receiver. Maybe not the input of the receiver, maybe at the output of the MRC. Alright, so SNR equals to what? Chi into P by sigma square. Yeah, this is SNR at the output of MRC. Alright, so L equal to 2 case I'm working out. Probability of SNR mod of H1 square plus mod of H2 square, because L is 2, right? So to P by sigma square. Alright. So what is the probability of deep fade what is the probability of, I need to figure out what is the probability of these two channel coefficients will go into deep fade. Alright. So this is probability of mod of H1 square less than 1 by SNR and mod of H2 square less than 1 by SNR. This is the probability I need to figure out. So this probability is basically the probability that SNR goes to 0. SNR is disastrously less. So we know that H1 square and H1 H2 are IID. H1 H2 are IID. So H1 has nothing to do with H2, H2 has nothing to do with H1. So mod H1 square has nothing to do with H2, and mod H2 square has nothing to do with H1. So these are also IID. So probability of H1 square less than 1 by SNR, H2 square less than 1 by SNR equals to probability of H1 square less than 1 by SNR into H2 square. I can basically divide the probabilities, decompose the probabilities. H1 square less than 1 by SNR into probability of H2 square less than 1 by SNR. Alright. So what is the probability of H1 square is less than 1 by SNR? We have derived it, which is 1 by SNR. And this is 1 by SNR. So which turns out to be 1 by SNR square. Alright. So this for L equal to 2 system. So similarly for L equals to 3, probability of mod of H1 square less than 1 by SNR, mod of H2 square less than 1 by SNR, H3 square less than 1 by SNR equals to product of all those things, probability of H1 square less than 1 by SNR into probability of H2 square less than 1 by SNR into probability of H3 square less than 1 by SNR. So we know this is 1 by SNR. We have to make sure this is approximation 1 by SNR. So 1 by SNR cube. So my probable, as for the given SNR, probability of all these 3 guys are going to deep fade is 1 by SNR cube in this case and 1 by SNR square in this case. So it is offering less probability of all channel coefficients going into deep fade. Alright. So I've done the performance analysis. So performance analysis also good. So let's do just to brief it up. I started with repetition coding. Basically, I'm sending the sim symbol x L times, or considering the fact that TD has to be greater than TC. So to make sure that H1, H2, H3, HL are IID, and why do we need that they have to be these channel coefficients have to be IID? Because it's affecting diversity order. Velocity is inversely proportional to coherence time, and we have written these equations, and we figured out the Mldecoder is MRC itself, and we figured out the rule, which is YA HI star equals greater than less than 0, which turns out to be what we are doing, which turns out to be it is nothing but MRC. Alright. So I've done the performance analysis of MRC. Again, I started with L independent channel equations. Multiply with the corresponding channel coefficients, add them up. I've added up, and I figured out there are 2 ways for you to figure out the diversity order. The first way is go through the longest path. Take assume this is BPSK. You derive the probability of error expression. Deal with the nasty equations, and you derive the probability of error expression. And if your probability of error expression will turn out to be 1 by SNR power something, this X is nothing but diversity order. Alright, and we took the easy path. The easy path is just to figure out the SNR, and which is much simpler. And we've done the statistics. We have worked out the statistics, and this is the crucial part. You have to know how to deal with random variables, and again re-emphasizing the fact this is H1 star N1 H2 star into HL star NL. So we know H. So H is essentially constant. So expectation of N, as expectation is linear, even if the random variables are dependent, expectation obeys the linearity property. So expectation is linear. Expectation of N1, expectation of N2, and expectation of NL has to be equal to 0. So expectation of N tilde has to be equal to 0. And also, they are independent. You can add all the random variable variances. All right. So H1, H2 are constant. If A has variance sigma, K into A has variance K square into sigma. All right. This follows from the same rule. The undergrad stuff. And sigma n1 equals to sigma n2 equal to sigma nl. So you can sum it up. Update. So signal power by noise power. I figure out chi, number of random variables, number of IID random variables, in the function chi is nothing but diversity order of the system. We need more diversity order. That's it for this video. Hope this helps. Thank you.